everyone to the weekly ITC Lunch. We just heard an excellent talk, I should say a brilliant talk, by Fred Rassio sitting next to me, so I'm not giving him compliments just because he can hit me. But he actually did convince many of us that the LIGO sources of dirty solar masses were predicted before they were observed, and that turns out to be indeed, it's agreed upon by the community. This is one of the rare cases where theoretical prediction was confirmed. So that should be recognized as a very important prediction. So we should all scrutinize it just to make sure that it's the correct interpretation. And Fred will talk to us, or actually talk with us at the end of this lunch, and he would like some advice about the future of publishing, but we'll get to that. So we have 4 presentations as usual. We'll start with Andrea Merloni, that will talk about the statistics of tidal disruption, flares, and dynamics of and the dynamic X-ray sky, followed by a talk by Lingham, who is a postdoc at the School of Engineering here at Harvard. I hope that Manasvi is somewhere here. Oh, he's over there. Great. And he will talk about artificial spectral edges in exoplanets. And then we'll hear from Keivan Stassun from Vanderbilt. I hope he's here. Yeah, great. Actually, I should mention that Keivan gave the Dudley Hirschbach lecture on increasing diversity in PhD programs. He's directing an important program, bridge program between masters and PhD at Vanderbilt, and this program dominates actually the PhDs of underrepresented minorities in the country, and he makes a very important contribution. One of the suggestions that Keivan makes is that is not to pay too much attention to GRE scores. And I should mention that as of the beginning of this week, the Harvard Astronomy Department decided to give up on the requirement for physics GRE. And so that was greeted with a lot of happy emails that I received. But at any event, Keivan is the CFA colloquium speaker today. And he will talk at lunch about evidence for 2 modes of radius inflation in active M-dwarfs. 2 modes of magnetic field topologies, perhaps. And finally, we'll close with Fred, who will talk about the future of publishing. So, Andrea.
Thank you. So the short story I'm going to tell you started about 3 years ago when 2 groups independently discovered a source of this weird family of changing look AGN that happened to be in the stripe 82 area, and so had a very nice light curve we could follow up, and we studied the properties of this light curve, this strong flare event from this particular AGN. We look at the evolution of the spectrum. This is the different spectrum when you subtract the galaxy, and so we came out with the interpretation. This was a tidal disruption event of a relatively big black hole of a 2 solar mass star. However, the problem with this interpretation was that this particular object had spectra taken twice during this outburst and show narrow emission line typical of AGN, so indicating that this source was an AGN at least maybe 10,000 years ago, the order of the light crossing time to the narrow line region. So was it possible to have a tidal disruption event in an AGN? We start thinking about statistics of how rare this event should be, or whether we were just mistaken this object for this was a normal AGN flare. So, of course, you can do statistics of TDE, you can do population synthesis studies. This is a nice work by Mark and MacLeod, and effectively here he simulates many different contributions to tidal disruption flares coming from giant stars, main sequence stars, and partial disruption. But the main message is when you know your triggering rate and you know a model for your light curve, for example, declining as a power law with a certain power law slope, gamma, then you can build the probability distribution. What's the probability to observe this event at a given luminosity? It's simple mathematics. It depends on the triggering rate, and it depends on the shape of the light curve, okay? So you can model your TD population, assuming the population of stars and some standard model for the light curve. What caught our attention is that X-ray people that do AGN surveys are now in the position to do the same. So to study probability distribution of detected nuclear sources. So this shows observational work from the Cosmos field, where we look at a completely identified sample of X-ray nuclear source. We all thought they were all AGN, and we studied the statistics of their occupation, how often a galaxy of a given mass hosts an AGN of a given luminosity, or in particular here I'm showing the probability of a galaxy of a given mass to host an AGN of a given specific accretion rate, which is defined as the ratio of X-ray luminosity to the stellar mass. Essentially, tells you how fast the black hole grows compared to the host galaxy. And lo and behold, this probability distribution are consistent with broad power laws, with the uncertainty that we have, and they don't seem to depend on the galaxy mass. It's kind of a universal triggering mechanism that, however, becomes more and more efficient at high redshift. So the chance to activate AGN becomes high at high redshift. This is also well known. And if you look at Lx versus this probability, the slope are -1. If you include bolometric correction, you can do the same. You can study the distribution of Eddington ratio, probability distribution of Eddington ratio. These are for different stellar masses, but the main point is that the data are consistent with the same distribution, which has a slope of almost exactly 1/5. Okay? So we try to put this thing together, and so this plot shows the expectation from the probability of a galaxy to have a nuclear source, okay, as a function of the bolometric luminosity of this nuclear source. And these three panels represent three black values for the black hole mass, 10 to the 6th, 10 to the 7th, 10 to the 8th. The solid red line is what we get out of AGN surveys. So assuming that all these nuclear sources are AGN, this is the probability distribution from observation. And this black line with the large uncertainty is the TD modeling that use some observational rates and assume that all TD decline in the same way. And so you can simply take the ratio of these two curves. And so for the AGN, I'm including some redshift distribution, but if you focus on the redshift 0 line, the ratio of the black to the red tells you the fraction of nuclear source that in any snapshot survey will be actually tidal disruption event. Okay? And this fraction is, of course, higher at low black hole masses, but it's around maybe a few to 10%. It's not a small number. The other thing you can do, this is for different black hole masses. Of course, the universe, you can fold it in the mass function of black hole. So you can convolve this distribution with a mass function and calculate the overall rate of the overall fraction of nuclear sources that could be powered by tidal disruption flares as a function of observables. For example, as a function of X-ray luminosity in the entire sample. Of course, things become more complicated because if you want to go from bolometry to X-ray luminosity, you have to assume something about what fraction of TD light comes out in X-rays. And this is not well known. So here, with three colors, I show three different assumptions. A very optimistic one in blue, where I say 1/3 of the bolometric TD light comes in the soft X-rays. The black is 10%, and the red is assuming that TD coronal generation is actually identical to AGN. So I gave the same bolometric correction of AGN. And this is for 3 redshift bin, but again, in the local universe, about a few percent of all soft X-ray detected sources are maybe, I mean, if you understand the rate, and there are big uncertainty, but maybe actually powered by TD. Okay, so given this, you may know that we've just finished building an MP, a big telescope that will do an all-sky survey in X-rays in the soft X-ray regime. It's called Rosita, and it's now been shipped to Russia for final test and integration. It will be launched in about 1 year time. And what Rosita will do is continuously scanning the sky and producing every 6 months a new all-sky survey. Quite deep, because the overall effective area of the telescope is as big as the XMM. It's one of the biggest ever built. So this is the interesting plot. It shows the expectation for the cadence, so the number of times each point of the sky will be visited by our telescope over 4 years. And most of the sky will be visited about 8 times. It takes 6 months for us to do an all-sky survey. Close to the ecliptic poles, due to our scanning strategy, the number of visits goes up to 20 over 60, close to the ecliptic poles. And because I told you the telescope is big, it's very sensitive. So each one of these visits over 4 years, we will be able to detect source as faint as 4 times 10 to the minus 14 ergs per second, which correspond to luminosity more than 10 to the 43 ergs per second within 1.5 gigaparsec, so redshift 0.3, or luminosity larger than 1.4, 10 to the 44 within redshift 0.7. And those are the typical peak luminosity of the few observed X-ray tidal disruption events. So the volume we have is huge, and the rates are not negligible. So my final plot is a prediction of the number of events that we will see, or at least that we will be there, and our task will be to identify them. And so this is the number as a function of redshift. For these three colors represent three different bolometric correction, optimistic, average, and more pessimistic. But these are the total, okay, when you integrate overall redshift. We are talking about at least about 100 tidal disruption events in our data stream per month, a few per day. And this is at the same time super exciting because it's going to provide a huge new window to understand this population and a lot of issue about stellar dynamics in the presence of black holes, but it's also very scary because to identify even a substantial fraction of them, follow them up, it's going to be a huge task that we have ahead of us. And we will be happy having people supporting or interested or even helping us in thinking how to best ripe, I think, this huge potential for science. Thank you.
Obviously, there are many other reasons for AGNs to get brighter in X-rays and then fade away.
Mm-hmm.
We don't expect TDEs, for example, above 10 to the 8 solar masses because that swallows the star oil. And another signature would be that it should be super Eddington for a short time. So did you think about ways of observationally discriminating these from flares that are due to changes in the accretion rate or other things?
Sure, of course. I mean, some of these effects, so the mass dependence, so how parameter of TD is embedded in the sharp cutoff that you have at high luminosity. This is exactly for the reason that high mass black holes don't have. In practice, one obvious way, at least in the history so far of TD searches, one of the first thing you look at is your light curve. And so, of course, because we were revisiting the sky a few times, we will look for signature of a certain decline. However, this may not be the whole story, just because some aspect of viscous accretion is triggering, and also the fact that the AGN power probability distribution has the same slope suggests that AGN can mimic a similar decline. But of course, another signature would be the looking at some longer-term properties in other survey data to see whether at the location of your flaring source you had activity ongoing previously. I mean, the big difference, if you think about it, is we don't know exactly what is the unit event time of an AGN, but it's probably much longer than a unit event time of TDE. And so you will be looking for signature, like in optical spectroscopy or in past observation, for things that have already been active substantially longer than a few years, which is probably the maximum time scale you expect a TDE to survive. Yeah.
Questions for Andrea? Other questions?
How serious is source confusion? I only saw briefly the pixel size, the field of view.
Yes. It's not big issues at this. So these numbers are taken from are the numbers of objects you get in one single pass, and one single pass is shallow. That means, shallow in terms of what we know about the log n log s. So in one pass you are very well away from confusion, and the PSF of Rosita is just a factor of 1.5, 2 worse than XMM. So it's not too bad, and we reach confusion at depth which are at least 10 or 20 times longer integration than what we are talking about here.
The importance of these large numbers is that we'll be able to tell which types of galaxies host them. There is currently a dispute about whether it's a special class of galaxies.
Yeah, I think right now we are in the phase that even the overall rates globally are uncertainty by almost order of magnitude, and the physics is in the rate subdivided by galaxy class, type, and redshift, whether it also is increased with mergers, or, there are plenty of interesting physical effects that theorists have been looking for, and I think observationally we are starved because the numbers of objects which we could statistically assess, is small. And at least I think this gives the potential to make progress, provided that we have the resources or the clever way to identify and follow up substantial numbers.
Some of the other very exciting things you'll see in these soft X-rays are novae and super soft sources turning on and off. Have you compared the numbers of those types of phenomena with these?
No, I'm sorry. I mean, we are going through the exercise of making educated guesses about all sorts of transients that we have both in galactic and extragalactic sky, and we have not finalized that. I mean, of course, there is pretty obvious, spatial separation between galactic and extragalactic that one could use somehow, but some numbers are, I mean, we will find there is a Merloni 2012 white book where we try to make predictions for what we wanted to do, but I think these are relatively rough. But sure, yeah. I mean, we to give you an idea, the depth we reach is such that we get a full picture of Magellanic clouds every month, new one down to 10 to the 34 Earths per second. So for variability science, X-ray binary science, it's going to be very exciting, yes.
Yeah, hello. Hi. So I'm going to be talking a bit about artificial spectral edges in exoplanets, and this is a work done in collaboration with Professor Abraham Loeb. And so first I'm sort of going to start off with sort of motivating what these are and so on. So first, the goal of this work is to sort of propose another means of looking for advanced civilization. So it's a form of SETI, search for extraterrestrial intelligence. And as we know, one of the most, an important aspect of exoplanetary research is to identify biosignatures and also to see, prospects of detecting them. And since the 1960s at least, since Lederberg and James Lovelock and so on, it's been known that life leads to chemical disequilibrium in the atmosphere. So you sort of notice some gases at much higher concentrations than you would otherwise. So a lot of the conventional discussion of searching for biosignature is focused around looking for these kind of gases in the atmosphere. These include examples like oxygen, methane, and so on. And however, the point is that some of these gases, especially oxygen, could be produced through abiotic means. And therefore, there have been studies trying to look for alternative means of detecting life. And one of the most well-known ones is what is known as the red edge of vegetation. And that sort of occurs because up to certain wavelengths, chlorophyll, or rather, leaves in general, absorb a lot of light, and beyond a certain point, they don't. So what you see is a sharp increase in the reflected light above a certain wavelength. I'll show you a picture soon after. But the point is that because you see this sort of sharp increase in the reflectance, it's been speculated that this could be, detectable and therefore serves as a viable biosignature. And there have been also other features which are potentially detectable through looking at photometric observations such as oceans, water, and so on. And so now we sort of get to the question, just as there is a natural red edge coming from vegetation, could there be something that is like an artificial spectral edge along the same lines as vegetation? And so as I mentioned, the premise here is that we are looking for advanced civilization. And of course, any advanced civilization will need to, will have a certain energy requirement. And so to meet that energy requirement, it needs a power source. And so we consider the case where, the power source is renewable and solar energy in particular. And we sort of focus on one particular form of tapping stellar energy, and that is via photovoltaic cells. And this is particularly advantageous on tidally locked planets, such as those which commonly, would exist around M-dwarfs, where on the day side you basically have continuous starshine because, it's always facing the star. And so what we look at is there a possibility of detecting very large-scale photovoltaic arrays if they were to exist on the planet? And then we sort of look at silicon in particular, and the reason we do that is because silicon is extremely abundant. I think it's the 7th most abundant element in the cosmos. And because of its abundance, it also leads to economies of scale, which means that you have lower processing costs and so on. But I should note that even for other materials, what I'm going to discuss in the subsequent slides will be partially true. For example, if you consider other materials such as gallium arsenide and so on, because silicon does have a few imperfections. Okay, so now I'll show you the red edge of vegetation, and I'll show you that for silicon. Okay, so the one in red is the red edge of vegetation, and as you can see, there's a dramatic increase in vegetation's reflectivity at around 700 nanometers, 0.7 micrometers. And similarly, one can see that there's a correspondingly sharp increase in edge in the silicon reflections, and that occurs at around 0.05 micrometers. So you can see that this particular shape is, very reminiscent of the red edge of vegetation. And so that brings up the question as to how one would detect it. And so the way of detecting it would be along the same lines as detecting vegetation. So you sort of look at the photometric observations over the period of time, and as the fraction of the surface covered by these photovoltaic arrays changes, you would see a spectralized contrast, and therefore you might expect to see modulations over time, which might give us an idea as to what fraction of the surface is covered by this silicon array, photovoltaic arrays. And here is a schematic figure which shows some of the secondary consequences that could arise from having such arrays present. For example, let us say that you do cover, this is the day side of the planet, and the one on the right is basically the night side. So let us say that you can have photovoltaic arrays on the day side. You can sort of basically use it to generate heat and light and then redistribute it to the dark side of the planet. And the advantage is that if you look at planets like these, it might turn out that the day side is too hot for life to exist, especially vegetation, and the night side could be too cold. As a result, the vegetation would be restricted to a very narrow strip. So if you can do this kind of an artificial redistribution, you can also use it to maybe grow plants or whatever on the dark side as well. So this brings up two different means of potentially detecting these kind of photovoltaic arrays. The first is directly by looking at the temporal variability, photometric variability, and trying to see whether you can deduce what fraction is covered. And the second is, as I mentioned, you might use the light you might use it to power light on the dark side. So you might have some anomalous lighting which might be detectable. And the prospect of doing that has been studied by some people, including Loeb and Turner and Corpella et al. And so on. So, and it's been suggested that Corpella et al. Suggests that it might be detectable by the JWST. And therefore, both direct and indirect means of detecting these kind of spectral edges. And this endeavor of looking for photovoltaic arrays is very closely related to what has come to be known as Dysonian SETI. So there's two different kinds of searches for artificial intelligence. The most common one is where you look for radio signals or optical signals and so on. And the other one is called Dysonian SETI, where you look for any kind of megastructures or artifacts and so on. And it sometimes also goes by the name of interstellar archaeology. But the problem with conventional Dysonian SETI is that it's restricted to extremely powerful civilizations, those whose power consumption is on the order of 10 to the power 33 watts to 10 to the power 44 watts. Those are what are known as Kardashev 2 or Kardashev 3 civilizations. And some of you might be aware of recent studies by Jason Wright, Stein Sigurdsson, and others, which deal with detecting Kardashev 3 civilizations. But our approach is geared towards detecting much more modest civilizations, which are more likely to exist. And so this is focused on detecting what are known as Kardashev 1 civilization, which means they can sort of have energy consumption of around 10 to the power, 10 to the power 16 watts or so. And these photovoltaic arrays, even though we've discussed them in the context of habitable planets, they may also exist on planets that don't have atmospheres. They could exist on exomoons, and they may even be part of other megastructures such as Dyson spheres. And although, as I mentioned earlier, although we've discussed it for silicon and for photovoltaic arrays in particular, you can sort of try to generalize it to include other materials. For example, the prospect of artificial photosynthesis or photovoltaic arrays using different materials and so on. So in general, this brings up the point that if there are advanced civilizations and they want to tap energy from their star, they would cover most of the fraction of their surface with distinctive raw materials which might have distinctive signatures, and these signatures may be detectable with future telescopes such as JWST, LUVOIR, and so on. And that brings me to the end of my talk. Yeah.
So this civilization is absorbing a large fraction of the incident sunlight and redistributing it. So
Right.
That's going to affect the whole structure of the atmosphere, isn't it?
Is it going to affect the atmosphere?
It would.
Yeah. I guess it would. Are you saying it would affect the atmosphere?
Well, yeah.
Yeah,
If you
yeah,
want to
sure.
compare the reflectivity of the silicon with that of water and land and so on.
Right.
And then you could put it into an atmospheric model, maybe.
Right. So I sort of didn't fully catch your question, though.
The atmosphere
Right.
is heated from the ground.
Yeah.
Right? So if
Right.
you're absorbing a lot of that energy
Oh,
and
yeah,
taking
yeah.
it away,
Right,
it would
right.
change the structure of
Oh,
the
yeah,
atmosphere.
sure. I quite agree. That might be another way of detecting such activity.
Yes.
Indeed, yeah. Right, and yeah.
Two questions.
Yeah.
First, on one of these, presumably you're considering only M-dwarf postcards. I think you mentioned that at the beginning. But if you are, I would think still just the long-standing problem of contrast of any reflected light from the planet versus the host star is a formidable challenge. So have you been through the numbers to show that you could possibly detect red edge or anything else?
So, we've sort of, it's sort of, partly a work in progress, but so the analogies with vegetation do exist, and so I should note that, it's not directly related to your point, but you may have seen that the edge is, on the ultraviolet side, and so it's not really doable by the JWST, but by things like LUVOIR, it might be doable. And so I think it's for Proxima b, for example, I think you should be able to detect changes up to a few parts per million. But Of course, as to whether it's detectable depends on a number of factors such as the viewing angle, the fraction of the surface covered, and also the cloud cover. So we haven't done a fully quantitative study because you need to take all of these parameters into account when doing so. Yeah, right.
My question was your view of where this fits in, because the type of planet you're considering sounds like for life to have developed on it, life have been difficult. So is your view that this is part of a planetary system and an advanced civilization is using this planet? Or does the civilization live on the planet?
Right.
I understand you
Right.
can't answer
Right.
the
Right.
question like
No.
this.
Yeah.
But I'm just trying to understand,
Yeah.
what context
Right.
you're doing the
Yeah.
problem in.
And no, that's a very good question. And so for that, I just want to say that here I've focused on a tidally locked planet where so life might exist only in a narrow region. But of course, in principle, this is applicable to any planet where life has originated and evolved. For instance, it's quite possible that humans themselves in the coming decades or a century could expand the use of photovoltaic arrays a lot more than we are doing now. And in that case, we could probably look at Earthshine and see whether we begin to see something different. So I would say that I think it's more likely that this would be applicable to civilizations that were born on that planet and evolved, and then they have more energy needs than they can meet, and they sort of rely on these kind of solar arrays. But it's also possible, of course, that they may have sort of migrated from some other place, from a different planet in the same system. For instance, as I mentioned, one of the things is you don't really need an atmosphere for this whole thing to be functional. So they may say, well, okay, for example, let's take Mercury and just, fill it up with photovoltaic arrays, and then tap that energy and use it to, send it to some other planet and so on. So there's a bit of flexibility. So looking at this, I mean, if one does detect these kind of distinctive spectral features, it doesn't mean that life exists. But it could mean that technology exists. So that's why I've used the word artifact. So if a civilization has moved on and, still left behind these arrays, it's possible that, they may still be detectable. Right.
Last question.
Yeah.
What's the magnitude of contrast change that you expect in your limiting case, roughly?
What's the
Well, I mean,
yeah.
if you go to your other figure, where you have the extreme case where one side of the planet's covered with silicon and the other side
Right.
has some strip of vegetation, what sort of magnitude are you looking at?
Right. So for the Earth, I think, again, I'm speaking of vegetation because, people have done observations. Like there's a famous paper by Carl Sagan where they looked at, at the Earth from the Galileo probe. I think they found a difference in the spectral, in the reflectance between 10 to 20% and so on. And I think other studies of vegetation have, typically shown that there's a change in the bond albedo by the order of a few percent, if you average over across all the wavelengths. So again, we haven't done the numbers for silicon arrays explicitly, but given that we are sort of trying to make an analogy between natural and spectral edges, so it's again possible that 10% of the Earth is covered by vegetation. So if you have 10% of the planet covered by photovoltaic arrays, you might expect to see, similar variation. Yeah.
You may have just answered my question, and that is what fraction of the illuminated surface needs to be occupied by these silicon arrays
Right.
In order for LUVOIR, for example, which I assume is the most sensitive telescope on the horizon, to distinguish it from a planet without solar arrays.
Right. Yeah.
Fraction.
That's a very good question, and so it's still a bit of a work in progress, and it's one of the things we would definitely like to think about. I don't have an answer yet, right? But it's a very pertinent point. So thank you for bringing it up.
Thank you
Yeah.
very much.
Right. Thank you.
Okay, hello, good afternoon. I'm Keivan Stassun, visiting from Vanderbilt. One of my current postdocs, Garrett Summers, and I have been thinking about the question of how low-mass stars come to be inflated, that is to say their radii come to be larger than expected from standard stellar models as a result of their magnetic activity. So let me start, just for broad context. This is a slide that you'll see in my colloquium talk this afternoon, just to set the stage. From studies of mine and others looking at low-mass eclipsing binaries with published H-alpha emission luminosities, we have established some empirical relations that link the amount by which an M-dwarf's radius is inflated, again relative to standard stellar models, here's a percentage of radius inflation, as a function of the strength of its chromospheric, presumably magnetically driven activity, here as measured by the H-alpha luminosity. And so you see that over this range of about a factor of 10 in H-alpha luminosity, you go from, according to these eclipsing binary stars, having radii that are not inflated at all to inflated by 10 to 15% or so. So this relationship between magnetic activity and radius inflation in M-dwarfs at the point of this work appeared to be relatively universal. We had one parameter, activity, that predicted an amount of inflation. But the story has become more complicated and more interesting with the recent release from the Mirth team of measurements of rotation, here represented in terms of Rossby number, rotation rates for a large number of M-dwarfs that have been monitored by the Mirth project over a long period of time. So for those of you who are used to thinking about stellar activity, this will be a familiar diagram. On the y-axis here we have a measure of magnetic activity, here again as traced by H-alpha luminosity. And on the x-axis, we have rotation rate in this funny sort of, this is an inverse rotation rate, basically. So these are the slow rotating inactive stars, and these are more rapidly rotating magnetically active stars. This is a sort of a typical feature that you see in this kind of diagram. And so I'm going to show you, and so this is from the Mirth team. So I'm going to show you a few more figures, and so just to orient you, in each of the figures, the red-colored points are these slowly rotating inactive stars. The white points are the more rapidly rotating magnetically active stars. So what Garrett and I have started doing is to ask, does the relationship, the roughly one-to-one relationship between magnetic activity and radius inflation that we saw in the eclipsing binary sample extend to this larger field population of M-dwarfs? And so we've used the parallaxes. There are parallaxes to the Mirth M-dwarfs. We've used the colors to estimate an effective temperature, and we used the parallaxes to get a bolometric luminosity, and so then the Stefan-Boltzmann law gives us the radius. Okay, so it's a quick explanation of how we've estimated the radii of these stars. Just to be clear, these are not directly measured radii in the way that we measure them for the eclipsing binaries, but we do have parallaxes to these stars. And so again, you see the red slowly rotating and active, the white, more rapidly rotating active stars. These are standard isochrones for M-dwarfs at various ages. And so what I want to highlight is that there is indeed this population of rapidly rotating active M-dwarfs that have significantly larger radii than their counterparts. If you were to infer those, if you were to try to infer ages for these M-dwarfs from these radii, you would think that they were extremely young, still contracting. These are old field M-dwarfs. That's not the case. Rather, they have inflated radii. Okay. But you also see that there's a whole mix down here of rapidly rotating active M-dwarfs, the white dots, that are sprinkled in the same region of the diagram where the slowly rotating inactive M-dwarfs are. And so we started looking at some other things. So here is, again, this measure of the amount of radius inflation. 0 means not inflated relative to the standard models. 10%, 20% inflation. Here is the H-alpha luminosity. So this is your measure of magnetic chromospheric activity. All right. So one thing that is clear and not surprising is that basically all of the slowly rotating inactive M-dwarfs are consistent with the measurement errors with being not inflated in radii. There's clearly this population of rapidly rotating active M-dwarfs that have significantly inflated radii. But what about all of these active rapidly rotating M-dwarfs that are not inflated or not apparently inflated? So another thing that we've looked at is the amplitude of the photometric variability in these M-dwarfs. And the amplitude of the photometric variability is usually attributed to the presence of star spots on the surfaces of these stars. And the reason that this is interesting, an interesting thing to look at, this is the same H-alpha luminosity quantity on the x-axis. The reason that this spot amplitude might be an interesting quantity to look at is that on the one hand, you see this clear relationship where the more chromospherically active the star becomes, in general, the larger is its photometric spot amplitude. That's not surprising, but it's a nice consistency check. The more active stars presumably are more spotted overall because they're more magnetically active, and so we get a stronger amplitude. But there's a second reason that this is interesting, and that is that depending on the distribution of spots on the surfaces of the star, you may get more or less photometric amplitude for a given amount of spottedness. So for example, if I put one big magnetic spot on the surface of the star, and that one big spot rotates around, I'm going to get a relatively large photometric amplitude because of the contrast effect is large between when I see the spot and when I don't. In contrast, if I put sort of a leopard print pattern of little spots all around the star, then at any given time I'm seeing lots of little spots, and so the overall photometric variation is small. And so what's interesting is that these rapidly rotating, magnetically active, inflated M-dwarfs tend to be relatively low amplitude compared to the other rapidly rotating magnetic M-dwarfs. So it suggests that perhaps the M-dwarfs that are rapidly rotating and active but also inflated are ones that perhaps have a more symmetric distribution of spots on their surfaces. One more piece of this is from recent work on Proxima and a pair of twin M-dwarfs in the GJ65 system. So now these are interferometric radius measurements. And so what you see is that here's Proxima. Proxima's radius for its mass is sort of what it should be according to standard models. These two GJ65 stars that have the same mass as Proxima are inflated in their radii compared to Proxima. It turns out that all three of these stars have relatively strong H-alpha emission. So they're all modestly active. The difference, however, is that the two GJ65 stars are spinning really fast. And when we apply our empirical relations for the amount of radius inflation that we expect for the amount of H-alpha emission that we see, the two GJ65 stars behave as expected. We can essentially correct their radii given the strength of the H-alpha luminosity that we see. But Proxima is different. Proxima has H-alpha emission, but is not inflated. And so, coming back to this diagram, there's this interesting difference between Proxima and its twins. As I mentioned, the GJ65 stars are spinning really, really fast. And so they behave in this inflated way with respect to their activity. Proxima is spinning quite slow. And so even though it is above this line for being active versus inactive, you can tell it's sort of right at the edge there. And so GJ65 and Proxima seem to suggest that there is indeed this transition, perhaps, a transition where there's some rotation rate above which an M-dwarf has to be spinning faster than some threshold in order for this inflation, radius inflation, to kick in. And so the last thing that I'll mention is that you might think that if there are two modes of radius inflation or not for M-dwarfs, that it might have something to do with their magnetic topologies. And I was convinced that that was going to be the answer. But there's this very, very recent paper that just appeared this past week showing actual magnetic maps of the two GJ65 stars that I just referred to. The two GJ65 stars are twins of one another, and they're twins of Proxima, and the two GJ65 stars are both inflated in their radii. But the two GJ65 stars have very, very different magnetic topologies. And I won't go into the details, but the upshot is that they have very, very different magnetic topologies. What they do have in common, however, is that the overall strength of the magnetic fields on the two GJ65 stars are very high. So that's where we're at looking at the relationship between radius inflation and activity in M-dwarfs. There is a hint that there's some transition where M-dwarfs can be active but inflated or not. And it really looks like that transition depends on the rate of rotation more than anything else. Okay. Yeah. Yep. Yep. That is roughly what we see. So, for example, at -4 in these units, let me start over here. At -4 in these units, you see this relation predicts a radius inflation of, what is that, 5 or 6%, and at the same point, a temperature suppression of about 2 or 3%. Yep.
So I realize this is probably a stretch, and there's a large difference in masses, but hot Jupiters are also inflated by about the same amount.
Yeah.
Have you thought at all about whether some of this physics might also apply there?
I have. I mean, I think the physics is probably pretty different. I mean, I think with the hot Jupiters, you're talking about an insulation effect, a heating effect.
That may be, but they're also spun up. So fast rotation may also be part of the spun up.
Mm-hmm. If they're magnetic.
Yeah, I was really interested in what's the connection between this magnetic activity and this expansion. Is it modifying the convection in some way?
Yeah. So
some people must have some ideas.
Yeah. So come to my talk this afternoon.
Okay.
Yeah. Well, I don't know that I'll explain it all. The short answer is that there are competing models. In essence, there's one family of models that basically treats this as an effect of heavy spot coverage, okay, so that you're sort of bottling up some of the emergent flux. And the luminosity is a nuclear process, down in the core of the star. That luminosity has to get out. If you're bottling up some of the flux at the surface by lowering the temperature, well, then the radius has to be larger in order to get the luminosity. Okay, so that's one explanation. But then there's another sort of family of models that are more along the lines of what you were saying at the end there, which is that it's more of a global, internal magnetic support process that ends up sort of cranking down the efficiency of convection, and so that it's a convection effect. And so it's not totally clear which of those is right. I will show you evidence this afternoon that suggests that it's the convection effect that's probably right. You should still come to my talk. Yep, good.